Our second presenter today is Edward Kluckowski. He's a PE. PE is the Northeast Regional Manager for Freyssinet, based in Sterling, Virginia.
Thank you for that introduction. I'm going to start off where Kurt Klink left off just before lunch. How many contractors do we have in the room this afternoon? By a show of hands, of course. Well, we got one, Dave. Okay. All right, well, I'm going to talk a little bit about Wallops Island from a contractor's perspective. And if I keep fading in and out here, I'm finding out, Paul, what you just experienced is a little tough with the height of us, right, to speak into this microphone. So anyway, Wallops Island Causeway Bridge over Cat Creek is the title of the presentation, and it's from a contractor's perspective. So for those that aren't familiar with Wallops Island, it's located on the eastern shore, eastern end of Virginia. It's just south of the Maryland state line, which I don't know if you can see my red dot there, but line's right there. The main Wallops Island station where the airport is located is there, and Wallops Island where the project was located, the facility was on that second item that I just pointed out. You can see here, again, there's the facility, and there's an actual overview of the flight facility. The facility itself was established in 1945, principally for launching rockets, both for government as well as commercial or private organizations. Launched over 16,000 rockets since its inception, and that probably averages over a little over 200 launches per year, I guess, once they started getting going there. And it has about 1,400 full-time employees. Project description, of course, the owner was NASA, and they were under they hired the Eastern Federal Lands Federal Highway Group out of Sterling, Virginia to oversee the project for them. The engineer of record was Clark Nexon, bridge constructed in 1959. Roughly 21 spans, averaging about 60 feet, with the center span roughly about 84 feet. Apparently, the first rehab of this structure was constructed back in 1986. And of course, from that point going forward, there were other inspections made in 2011. And of course, during that time, concrete delamination, surface spalling, post-tensioning system deficiencies were identified on some of the spans to include both span 8 and 11. And the project goal, which I find is kind of interesting, and this is something that probably pertains to most of your DOT-related folks, is that the owner requested that the recommended repairs prolong the life of the bridge for another 10 years. In other words, they didn't want to go full bore with all of the repairs when they get it up to about 10 years, because during that time they plan on replacing this structure. So please keep that in mind as you look at some of your projects in some of your areas. And in our case, the project duration was August of 2013 through June of 2014. So this is just a brief plan and elevation of the structure. You can see 21 spans from left to right. You can see the elevation as well, about 40 feet over the intercoastal waterway, which is the high point of the structure. And that really doesn't do it much ado, because I'm going to show you a picture here. You can see one of the reasons why the owner did want to eventually replace this structure. This is a side view of the bridge. You can see that there's a lot of communication as well as electrical and water lines that connect the mainland out to the launch facility. You can also see, hopefully from this shot, that there are some pending repair areas. You can see some of the prior work that was done on the structure and some new instances where the bridge is starting to corrode some. Here's what I was talking about. Although it's 40 feet over the intercoastal waterway, one of the issues the owner had was if you're standing down at the base of this structure, really it's kind of tough to see what's coming at you. And if you were on the other side of the bridge and they have a rocket being moved in a large vehicle coming your way, it's going to be awfully scaring if you're on the other side of that bridge and all of a sudden the rocket starts to appear right over the crest. So they really wanted to increase the sight lines of the structure. Or I should say they want to increase the sight lines of the structure once it's replaced. So work performed, we performed roughly 239 square yards of concrete repair, mainly in the superstructure, just a little bit in the substructure. Repairs to existing, I should say, external post-tensioning strand, not the pre-stress strand, and I'll clarify that later. And also from a beam strengthening standpoint and also protection standpoint, we placed roughly 4,200 square feet of carbon fiber for flexure strengthening, and also roughly 9,300 square feet of glass fiber reinforced polymer for the protection. In addition to that, we applied a UV top coat over that glass fiber material. And then, of course, one of the biggies, as you could probably tell from those pictures I showed you earlier, was the maintenance of traffic that was key, because at some point we did have to bring construction vehicles onto deck in order to access the work areas. So here is a shot of one of the plan details. You can see from the charts, the two charts on the right-hand side, that pretty much dictated the type of work that we were going to do. It was either a glass fiber repair, or it was also a glass fiber in combination with a flexural repair, i.e. placing carbon fiber on the bottom flange of the structure. And of course, from the drawing itself, you can see there's a cross-section A, a cross-section B, and depending on where we were on the beam, dictated what type of material we were to place. So here's a shot of, I believe this is span, it's tough to read from this angle, it's probably span 8, where some of the loss of strength or flexure in the beams took place according to the last survey inspection. And you can see in this particular case, the beam that we inherited to repair came with about 2 inches of gunite on the bottom of the flange, and then below that were 4 external post-tensioning strands that were obviously anchored on either side of the beam. And of course, in this particular repair, the engineer of record, in this case Clark Nexum, was assuming that there was probably somewhere between 4 and 6 strands that were broken, pre-stressing strands that were broken, and then in order to replace that strength, a corresponding amount of carbon fiber was added on the bottom flange in order to bring some of that strength back in lieu of those broken pre-stressed strands. And also one of our requirements was to determine, as we remove some of the deteriorated concrete, determine just how bad or how deteriorated or broken the pre-stressed strands were. And if in fact we found that there were more than 2 in this particular case, or more than 6 in the prior slide, then we had to consult with the engineer of record and the Eastern Federal Lands folks to determine if we needed to add more carbon fiber material. So this is span 11. And you can see the same type of scenario. In this case, 2 external post-tensioning strands, which required 2 layers of carbon fiber material for flexure, and of course the glass fiber surrounding that once the carbon fiber was in place. And incidentally, the external post-tensioning strands did stay in place. We had to work around those, and you'll see that it wasn't too hard of a job to do that based on once we removed that gunite material. So the typical areas requiring repair, as you can see from this slide, that's just a shot of one of the pier caps. You can see some of the rusting, which is obviously a prelude to what may be occurring underneath the concrete surface. And then, of course, just another close-up shot, as you probably saw in the prior presentation. Now this one, a lot of deterioration taking place, and some of that which we needed to remove and replace with new repair mortar. And from this particular slide, in addition, you can see, in this case, back several years ago when they performed the last repairs on this, there was a 2-inch layer of gunite that was applied to the underside of the flanges for some reason, which I don't know. And in this particular case, and in most cases throughout the structure, you could see where there was cracking that was occurring between the interface. So not sure how it was applied, but of course, perhaps the original intention of thickening that up, maybe giving it some more load carrying capacity, in this particular case was starting to fail because of the cracking. So underneath the structure, you can see obviously the first part of our job is to start surveying the areas that were showing some deterioration, marking them off with red lines and so forth, orange lines, and starting to chip away that gunite that was found on the bottom of the flange. In this case, we removed the gunite. You can see some of the poor condition of the material that was already in place. And of course, you can start to see some of the condition of the pre-stressed strand. Just another close-up shot. Again, the gunite removed. You can see the gap. I'm not quite sure what this is. Maybe it was a makeshift deviator or something. back in those days. And you can also start to see some of the condition of the pre-stressing strand. So once we started to uncover this, we started to dialogue and communicate with the engineer of record and also the client to determine just exactly how much carbon fiber was going to be put back into place. Now, of course, none of this work can be done unless we have a good work platform by which to conduct the repairs with. And this is the start of us going ahead and putting in a temporary repair platform. In this case, we were working with a company out of Western New York called SafeSpan Platform Systems. And you can see from here they're starting to go ahead and put in their initial support lines to support the deck that we work from. Here's another close-up view. Again, you can see those power lines, water lines, and so forth. Those are always a contractor's nightmare as far as trying to access the bridge from up top underneath. You can see here that we have the support ropes going out. You can see how they're tied into the piers. You can also see the ropes underneath the piers that will support the corrugated metal deck that will then start to go into place. Also, in order to access a couple of repair areas that we had on the substructure, we also had a platform system, which you'll see in this slide, or excuse me, the following one, but you can get an idea of the platform taking or going into place. Also note, you can see where the gunite, the existing gunite was still on most of these beams, and you can see the outline of the external post-tensioning ducts. And also in some cases you can see there's actually daylight coming through those. So again, you kind of wonder what the purpose of those was, or they just simply weren't maintained over the years. Here's a picture of that platform that we used to make some repairs along those columns on the bridge. Pretty nice sturdy system. This is crucial for at least contractors as far as gaining access and also making proper and timely repairs and quality repairs. So some of the challenges that we had with this project, we unfortunately got a little bit of a late start, and so that took us into the late fall, early winter, and of course in this part of the country it does get fairly chilly at night. So one of the things that we needed to implement was a weather plan that made the work environment, one, safe for our workers, but also allowed to keep the temperatures in the areas that we needed to work at a decent temperature in order for the carbon fiber, glass fiber to bond. And typically most suppliers of these materials recommend something right around the 55, 60 degree surface temperature mark in order for those resins and carbon or fabrics to set up and form and sit in place. So not only do we have that to deal with, which we dealt with from the platform, we also had plastic sheeting and torpedo heaters that we needed to apply in order to maintain that atmosphere. Also with the carbon fiber, especially from the flexural standpoint, we needed to ensure that we had flat, consistent surfaces on the bottom of those flanges. In addition, we had to worry about road and bridge closers. There were a couple of different rocket launches that we had, so those shut down the structure for a couple of days, moving parts and pieces and equipment over to the launch pad. And of course, the work platform itself. In this case, we got a little bit of a late start because of a subcontractor issue, but just the initial setup process was a challenge in the beginning. So this is a shot above, or on the deck, I should say. You can see an example of one of the torpedo heaters that supplied warm air down to underneath the bridge deck into the work areas where we were. And you can also see some of our access points for our workers that allowed them to climb up a ladder and down and into the platform that I showed you earlier. And here's just another view of the structure once all this is in place. You can see somewhat of a rather elaborate system, and you can only imagine those are pretty big heaters and what we needed to spend in fuel to keep those things going for several months during the cold weather. So prior to us starting the work, and in fact, and probably in the beginning of the job, one of the things that the contractors typically responsible for is putting together a shop drawing that involves the use of the carbon fiber and in this case glass fiber as well. So this is an example of a drawing that we noted how many layers of carbon fiber fabric that we're using in this particular example. In this case it was three layers of carbon fiber material. And of course when it came to rehabilitating the post-tensioning ducts, we were required to put one layer of glass fiber around those ducts. And of course, the glass fiber itself encapsulated that area, the top of the flange, bottom, and the other side of it. And of course, the post-tensioning ducts were left in the position that we found them in once the gunite was removed. So with that shop drawing in play or approved and us moving forward, we now move into final preparation of the concrete surfaces. So you can see here, we've finally removed a lot of the poor concrete. We've squared off some of the repair areas. We've removed a lot of the materials, concrete materials that were surrounding some of the corroded steel, cleaned up the steel, obviously paying very close attention to the pre-stressed strands. And of course, from there, we continue to refine that, and then we come up with a finished surface that we feel comfortable with as far as placing the carbon fiber and glass fiber materials on. And here's an example of that finished surface. Again, what we're looking for is an ICRI surface preparation value of either a 3 or a 4. Again, you want to have a good mechanical bond between your polymer and your glass and your carbon fiber materials. In this particular case, I would say this surface here is probably not prepared enough yet, but we'll get there. And also, you can see how we also rounded the edges of that astio girder, because typically you have to have at least a minimum of a 1/2 inch radius, or 1/2 inch radius, so that you don't have any sharp arises that could potentially penetrate the carbon fiber or glass fiber over the years as loading is applied to the member. So for some of you that may be new to some of this FRP, I threw in a couple of slides. FRP is typically a 2-part system. The primary fibers used today are either carbon, glass, or aramid. And you can see in some of these cases, depending on the type of material using, a bidirectional typically will allow you to work around irregular surfaces to some cases, depending on how big and how closely spaced they may be. And of course, the other part of the system is the resin. 2-part resin. You can see from this slide, you have a smaller can and a larger can. That helps the field personnel ensure that they're going to mix the right cans together, which is critical. And then, of course, the goal here is to encase the carbon fiber or the fabric with the polymer resin in order to, and adhering it to the concrete to give it the strength-making properties. And why use the FRP? Of course, you've seen a lot of this, and you've seen prior presentations, all types of damage that's occurring out there, from shear issues to just deterioration on the ends to confinement issues. So the fabric can be used in a lot of different cases. And if you remember from years ago, for the old timers out there, we used to use steel plates. So you can only imagine what it was like putting steel plates above your head on a structure. Wasn't very easy to do, and of course, it certainly wasn't light in weight. And again, there are some various types of techniques, as you can see from this particular slide, openings in floors to confinement to shear strength, a lot of different applications for the material. And of course, there are several advantages, as I may have already pointed out, but one that's driving this is economics. It's definitely a lot more economical than replacing or adding additional steel and concrete, at least we've found when we've estimated projects. Certainly the strength to weight ratio and of course ease of installation in some of these structures far supersedes the concrete steel alternative. So back to the placement of the carbon fiber material, you can see one of the key things is getting your repair work area right into the, or excuse me, your repair equipment right in the area we have to place the material like these guys are doing. You can see we have a nice board laid out where we're cutting the fabric to lengths. This is the carbon fiber material that will be placed on the bottom of the flange. And then from here, we've put an application of resin, epoxy resin on the bottom of the flange. And then, of course, we've got a light coat of that on the fabric itself. And now we're starting to put that in place. So notice the various safety equipment, obviously you have to use from the smell of the material. And obviously it gets a little dicey at times with all that polymer on the fabric and so forth and trying to put it in place. But they are putting it in place with steel rollers and spatulas that help spread out the material. And of course you want to eliminate all types of air pockets and things of that sort to ensure that you have good adhesion to the bottom of the flange. I don't have any photos of putting the glass fiber up, but that's an example of where we left it. So in this case, you have glass fiber on the bottom flange, and you have the glass fiber on the surface that you now see, and of course note the rounded edge of that girder, which is key. And there's a finished shot of the project. You can see right there, followed by some of this. And again, a UV top coat put in place, obviously to protect it for upcoming years. And then just another shot of the project. And that concludes my presentation.
Do you have any concern about wrapping it fully for venting or moisture release in the
That's a good question that typically comes up. In this particular case, in this particular job, it was not an issue, so we put it per specifications requirements. But what Paul's referring to is sometimes we have seen issues where if you're going to fully encapsulate a structure, you typically may want to consider putting in a spacing of 1 inch, maybe 2 inches between carbon fiber or glass sheets so that that concrete can breathe or let moisture that comes in from the top of the member escape at the bottom. So I think some states may have experienced cases where they have not let it breathe and they potentially cause issues.
In regards to carbon fiber, I actually got into it back when Tony Onani, when he was back in Missouri, started using CFRP and GFRP for bridge strengthening. Of course, the issue becomes that if your bond is not any good,
Right.
then you lose the strengthening. So I was just wondering if you did any type of NDT testing, whether it was impact echo or acoustic ultrasonics, to verify the bond between your FRP and your concrete.
We had some what they call test strips along the way for that carbon fiber. Typically, you'll take your adhesion test right in the area that you're currently working in order to test whether or not we've prepared the surface properly and put the epoxy resin in. So there were several test strips along the way that we used in order to verify what the bonding strength. Yes.
So in your system, I see you use both the carbon fiber optical and glass FRP. So what's the advantage of use both material rather than one single material?
If I understand the question, the carbon fiber was used to improve the flexural strength of those asteel girders on the bottom of the flange. And the glass fiber, the way I understood it through the designers, was simply just a protective mechanism to keep the elements off of the bottom of the flange, i.e. where most of the pre-stressing strand was located at. And that's what we see in a lot of, at least maybe in the mid-Atlantic states, especially in Maryland as an example, where they're putting a lot of glass fiber up to protect the concrete and the reinforcing steel underneath it. So I'm assuming that in this particular case, it was the same as what we're seeing on other projects that we see out in the various DOT regions.
We've also seen when you apply it and during that resin drying that bubbles form and had issues with that. How do you mitigate that over such a large surface area?
It's a skill, and you have to have the right tools. Typically, we use metal rollers in combination with very large but stiff spatulas, for lack of better terms, where we're constantly moving those in various directions to push out air bubbles from the center line out to the closest distance we can get them out, and constantly do that until we feel comfortable that we have eliminated that. And of course, if you do experience one of those bubbles, there are repair methods from many of the material suppliers that, based on maybe a 3 inch by 3 inch area, you can inject those areas. There's several different repair techniques that you can apply without having to remove the material, of course, that help you get around it if you experience that.
My understanding is you used carbon fiber to restore strength to the asteel girders.
Yes.
So did you use it only for girders that have not experienced spalling yet, or do you use it also, do you patch the ones that experience spalling and just not worry about grabbits for the strains that are missing?
I think in this particular case, when the survey was initially done by the engineer of record, their main concern was the carbon fiber was going to be used depending on what they found the condition of those pre-stressing strands in. So depending on either if it was 2 strands or less, or 5 strands or more dictated the amount of carbon fiber that they would use for that flexural strength when the repairs were made. I'm not sure if that answers your question, but of course, maybe along with that, making the proper concrete repairs, ensuring that that concrete is cured, and then coming back and preparing the surface and applying the carbon fiber was critical in this. So there was some wait time before we could do all of those steps. But that was the primary concern. This is the first time where we've had a situation where we just reported out the condition of the strand, pre-stressed strand in this case, and then the engineer of record and the federal highway guys came back and said, well, add another layer of carbon fiber as an example. Normally, we're the ones making the calculations and pointing out to them what we need to do, but this is just a little bit of a unique job in that sense.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.